All right, exercise 6E, example 1. Let's sketch the graph of this function. First question I want you to start asking yourselves. How many brackets are there and why are the brackets important? So how many brackets can we see in this example, Namafi? 1. So if you see only one bracket, what does that imply? What does that imply? Because that's meant to tell you something. In fact, I know two things when I see one bracket. What am I expecting? One x-intercept, right? And then I say, all right, well, this only has one x-intercept, so write a note, one bracket, one x-intercept. But then I ask myself, well, what type of shape is this? So I look at the power or the order or the degree of what this polynomial function is, and clearly it's cubed. So if it's cubed, it must be not a quadratic, not a linear, it has to be cubic. Now from last week when I mentioned the shapes, we know a linear is a straight line, so that's power of 1. We know a quadratic, which is parabola, or parabolic, it's x to the power of 2. Cubic looks like this. It's asymmetrical. It's the opposite of a symmetrical shape like a quadratic. So it's asymmetrical, goes the other way, the other direction. And this is where you can have multiple x-intercepts depending on how you change that little inflection point here. Okay, so there's a point here called the inflection point. This is what a cubic graph looks like. So x to the power 3, this is what it looks like. If you have only one intercept, then you expect the x-axis to only cross once. So because it has only one bracket, I do expect it to look of something like this, or maybe it touches the x-axis down here. Who knows? Okay, but I just know it touches once. Regardless, that's the shape. If there were two brackets, if it was a two bracket scenario, one's a linear, so let's say x minus 1, and then the other one is x minus 4, but then this one's squared. Again, that's quadratic, but then quadratic times a linear will make it cubic. But this tells me how many x-intercepts if you have two brackets. How many x-intercepts do you expect, Artie? 2, because you've got two brackets. And the only difference here is what does that square do to the graph again? Anyone remember? What did I show you last week? When you have a square on one of the brackets, what happens? What happens? Because we know when it's just a bracket, it crosses through. Yep. Yeah. So in this case here, usually if I asked you what's the x-intercept, you would have said x equals 1. If I asked you what's the x-intercept for this one, you would say x equals 4. So that means if I put it, there's 1, there's 4, but just like Namafi said, there's going to be a turning point right at x equals 4. So it has to cross through 1, and it has to come back and then turn at 4. Whoops. Has to be like that. So it's a cubic. You can see how I'm taking this shape and I manipulate the shape. There's always a bottom part, there's always an up part. It's asymmetrical. And it will always have, depending on the number of brackets, it tells you the number of x-intercepts. That's what you're doing in 6E. Cool? Let's do some examples. So I'm going to just delete that just so that you know what you're looking for. So I'm saying one bracket, one x-intercept. I know it's cubic, so this is what it looks like. It has an inflection point. Now let's read it. We have this plus 1. What does the plus 1 do again? Anyone remember what's plus 1? Let's go with Massey. What's plus 1 do to the graph? Good. Goes up by 1. Very good. What does the x minus 4 tell me, Sion? It is what? No. It would have been if there wasn't the plus 1. But what? Left or right. Very good. So just like your quadratics, your turning point, it tells you left or right. And one of the techniques I told you that you could find out. What was the technique I told you? There's only one unique technique. No one teaches it this way, only I do. How do you know if it moves left or right? What do you have to do? Yeah. This is what I told you guys. I said let it equal to 0, and I told you to solve for x. If you solve for x, it equals 4. If it's positive, it goes to the right. If it's negative, it goes to the left. Don't question it, because I haven't taught you transformations yet. This is just my way of teaching it. It's technically not mathematical and not true. but it's a way for you to remember. Okay, so this tells me right by 4. So if you want to sketch this now, we know this is your shape. We know it has an inflection point. Goes up by 1, goes to the right by 4. So let's follow that. Up by 1, to the right by 4. So it's over here now. So it's gone up by 1, to the right by 4. And then from here, I know it has to have an inflection point. The problem is I just don't know where the y-intercept is or where the x-intercept is. So for all I know, it could look more like this. It could look like this. I don't know. All I know is the inflection point is right here. So this is why you need to find x-intercept, y-intercept. Now y-intercept is easier to find. Y-intercept is let x equal to 0. Here we go. We've got y is equal to x minus 4 cubed plus 1 becomes 0 minus 4 cubed plus 1. And what's negative 4 cubed? Negative 64 plus 1 is negative 63. So clearly in this diagram, negative 8 is too short. So negative 64 must be really, really down here somewhere. So when you sketch it in this one, you can't really see it. What about the x-intercept though? This is what you've been training to do. X-intercept. This is when you let y equal to 0. So y has to be 0. You've got x minus 4 cubed plus 1. See, and these notes are from last lesson, that booklet. So if you find that booklet, you should be able to copy it down. How do we solve this? We're trying to find x. Using algebra again. You want to do the inverse of everything. So what do you see that's the easiest to get rid of first? Anthony? Yeah. Do SAMDOB. Opposite of BODMAS. So go backwards. Any subtraction, addition. So I would say subtract 1 on both sides. 1 take away 1 cancels out. You now have negative 1 is equal to x minus 4 cubed. And up to this point, a lot of students get scared or confused. What's the inverse of cubing? Yeah, cube root. So here we do cube root. Cube root of cube cancels out. That means you have to do the cube root of negative 1. Now, I just taught my year 8s this one as well, except they weren't doing negative numbers. But I said, what's cube root of 1? Cube root of 8, cube root of 27. Cube root just means what's a number that times itself 3 times to get you negative 1? What's the number? Yeah, negative 1. So this now gives me negative 1 is equal to x minus 4, and we're almost there. We're trying to find x, so opposite of minus 4, add 4 on both sides. That tells me x must equal to 3. So based on what I can see is I've got the shape. I know it has one x-intercept, which conveniently was here. That's at 3, 0. Inflection point I've already put in. And I know that this is a positive shape because the number in front, or if you cubed the x, it's a positive x cubed. So it's always going to go up rather than going down. Okay. So if I were to draw it, I know the shape must look something like this. And unfortunately, you can't see the y-intercept because it's too low. It's at negative 63. So it's really, really down. Yep.
When we sketch, do we have to like the inception point, inflection point?
I don't usually see them do that, but I usually draw it so that it looks like that's where it curves. An inflection point essentially means it changes the direction of what they call concavity. And that's a bit of a big word for you guys to sort of know. But what it means is, you see how the gradient is really high, but as you get to a certain point, it starts to get flatter. Flatter, flatter, flatter. So it's obviously getting smaller and smaller and smaller. But at some point, it changes direction. It gets larger and larger and larger. An inflection point means at that very moment that it goes from small to large, it changes direction. That's what an inflection point means. Okay, so the inflection point is there. So I just make sure that when I draw the shape, it kind of shows that the inflection point occurs at that point. Yeah, but you won't get penalized if you don't put in the inflection point. Yeah. So far, so good? Let's do another one. Next page. All right, and then once you do a couple of these, you'll then remember back in quadratics, you'll be like, why didn't I get it? Because I did a few of this in your SAC, and a lot of you left it blank or like you did it all wrong. But then you look back and you're like, oh, actually, it's pretty straightforward. Let's have a look at this one. Same idea. If I asked you, how many brackets does this example have? I know I didn't put the brackets, but you can imagine where the brackets would be. How many brackets do you see now? Try to picture it. Luke? 1. Even though we don't put it, it's actually just here. It's x cubed. See, the other one was x minus 4 cubed, but that's because we had to the right by 4. Who said I have to go to the right by 4? I could just leave it there. So it could have been x minus 0. But if it's x minus 0, this is what you'd get. So in a way, this is implying the 3 brackets when you do a cubic is x times x times x. Get me? So technically, there's only one bracket there. So if there's only one bracket, that implies one intercept. Now let's read it. What's a minus 8 do? Anyone? What's minus 8 do? Down by 8. Exactly what you've been doing. Exercise 3D from memory. 3D from chapter 3. So down by 8. But you can see again, this is a cubic, has a cube. So I know the shape must again look something like this. It moves down by 3. Oh, so down by 8. And it doesn't move left or right. So if you had to sketch this, down by 8 goes all the way down, and here's my inflection point. 0, 8. It should only have one x-intercept because you're only cubing this x. That is the bracket that we're looking at. So that means you can expect the shape to look something like this. Something like that. I just don't know where the x-intercept is. I do know where the y-intercept is because it clearly is at 0, 8. So I don't know if it looks like this. I don't know if it looks like this. That's why we need to find the x-intercept and y-intercepts. In our case, y-intercept's already given because we happen to figure it out. If you let x equals 0, you would have got negative 8. So we already know that the y-intercept is at 0, negative 8. X-intercept is what you need to figure out. X-intercept is y equal to 0, so you got x cubed minus 8. From here, you can use the skill that I taught you, difference of cubes formula, or you can just do what I've just been teaching you, inverse operations. Opposite of minus 8, add 8 on both sides. 8 is equal to x cubed. And then finally, to get rid of cube, the opposite of cubing is not square root, cube root. Very good. So we cube root the right, cube root the left. These cancel out. And what is cube root of 8? 2. Very good. So that tells me when y is 0, x is 2. So here's my x-intercept. 2, 0. We know it's cubic. We know there's only one intercept, so it must look like this. So if I were to sketch it, whoops, it should just look, oh sorry, the inflection point's down there. Maybe it's easier if I try to do it like this. There we go. Oh, that's bad. Let's do it again. Inflection point, oh, inflection point. There we go. Something like that. So far, so good. This is exercise 6E. So 6E has only one bracket. 6E is just left, right, up, down, and you're doing the same thing over and over. So it's meant to be easier than 6F. Okay? All right. Now, this last example, I haven't taught you this, but in the notes, you can probably figure out what you need to do here. What kind of function is this? The power is to the power of a third. That's cube rooting. So this is called a cube root function, right? But even if you don't really know this fully yet, you can still read a couple of things. What's a minus 2 do? Down by 2. What's the x minus 1 do? Right by 1. Very good. So You just need to know what the shape looks like. We know it's positive. We just don't know what a cube root looks like. But I did give it to you. If you scroll back up or go all the way back up, I gave to you, if this is what a cube looks like, this is what a cube root looks like. And a way to remember it, if you tilt your head, it kind of looks like a cube is just reflected on the x-axis. Okay, so they're both very similar. They're both very similar, as you can see. One is like an N shape, and the other one's like an S shape. Okay, so if it helps you, write a note, say cube root is an S shape. Okay, same idea. So inflection point is at 0, 0. Same idea. Instead of going up, it's now going right and left. Cool. Let's try to sketch this. And we now know it looks like an S shape. So I'm going to draw on the side. This is what it looks like. It looks like an S shape. Inflection point and S. Yeah? You told me it goes down by 2. Here we go, down by 2. And then right by 1. So here's my inflection point. I've got it at right by 1, down by 2. I just don't know where the x-intercepts and y-intercepts are. I know it looks something like this. It's an S shape. So all I know, it could have been like this. It could have been like this. Who knows? We don't know where the x and y-intercepts are. That's why we're going to figure it out. So here we go. Let's find it out. Y-intercept is when x equals 0. So y is equal to 0 minus 1. Cube root of negative 1 minus 2. What's cube root of negative 1? Negative 1. It's minus 1 minus 2. Y is equal to negative 3. So for those who are unsure, I'm just going to write a note here in case you're not familiar. This means cube root. Okay? To the power of a third is cube root. So y equals negative 3. Your y-intercept is at 0, negative 3. Now we know it definitely crosses here. So your S shape has to cross at 0, negative 3. To find the x-intercept, it's when y equals 0. So here we go. 0 equals x minus 1 cube root minus 2. All right, let's see if you guys can figure this one out. Bit of algebra. What's the first thing you're going to get rid of? Sam done. Yeah. Opposite of minus 2 is add 2. Add 2, add 2. Negative 2 plus 2 cancels out. 2 is equal to x minus 1 cube root. And this is where I'm interested. How do you get rid of cube root? What's the opposite of that? Yeah, it's as simple as that. Cube the right, cube the left. Cube and cube root cancels out. Or if you remember your index laws, a third and 3, you times them together, it gives you 1. So your answer ends up being x minus 1 is equal to 2 cubed, which is 8. And then from here, we all know, add 1 on both sides. And x equals to 9. So that means 9 is way down here somewhere. I don't know where it is. Let's just say it's over here, roughly. So 9, 0. So if you had to draw this shape, this S shape, it's a bit harder to draw now. Oh, there we go. Looks kind of like that. There we go. Something like that. It's a very thin S shape. But the idea is pretty straightforward once you know the shape. Get me? The whole idea is about knowing what type of function do you have, and once you know what function you have, you're just reading transformations. That is exercise 6E. So far, so good. Because we're going to move on to 6F, where I'm now going to show you different brackets. All of this has one bracket. Okay, notice this one only had one bracket, so there was only one intercept. That's how you know. Number of brackets is the number of times you can factorize them. Number of linear factors tells you the number of x-intercepts you can get. Cool? All right. As you're copying, anyone still needing to copy before I move on to 6F? Yep. This one? Oh. I don't know if I have any spares. Oh. Oh, you're lucky. I think this is the last copy. You lose this one, I ain't got to print another one.
Thanks, sir.
All right, 6F, we go. Did I do some of the examples with you? Let's see. How many examples? Oh, I haven't. All right, cool. Let's fill these ones in. All right, can you turn over in your notes to 6F? Exercise 6F. In that booklet, let's do this example together. First thing I want you to figure out is how many x-intercepts do you expect? How many x-intercepts do you expect in this example here? 3. Very good, because there are 3 brackets. Then where would the x-intercepts be? X minus 2, x should equal to? What should x equal to? For the first one? If x minus 2 is a factor, what would the x-intercept be? 2. Just in case you don't know how I knew that, you let y equal to 0, so 0 equals to x minus 2, x plus 1, x minus 3, and you do exactly what you did in chapter 3, null factor law. This times this has to equal to 0, so one of them has to equal to 0. So it might have been x minus 2 equals 0, so then if you solve for it, x-intercept could be at 2. X plus 1 could equal to 0, so that means x equals negative 1. What about the last one? X equals to? 3. We have 3 x-intercepts that we can expect. So we've got 2, I'm going to label them, 2, 3, and negative 1. Now notice on the bottom I put a diagram for you. I called it a sign diagram. In your exams, we can do this probably next time, but in your exams, the question usually asks you, how do you know that the shape will look like this? Or will it look like this? Which one should it be? Okay.
It should be the first one that you did because it's positive.
Yes, and that's how I usually like to teach you guys. I like you guys to look at it in terms of if you expanded the brackets, x times x times x is going to give you positive x cubed. If it's positive, we know that in the long term it has to keep going up. So that's the logical way. In the exams, they'll ask you to justify. That's why we use this technique over here. Okay, but ignore that for now. I just want you to analyze through the equations. If you can learn reading through the equations, then it saves you time from doing that. Okay, I'll show you that next lesson. All right, team. So I know it has to look something like this, but if you're unsure, let's say you can't read whether it's a positive graph or not, find your y-intercept. Your y-intercept will prove which one it should have been. So if you can see here, if I drew both of them again, you either have a y-intercept that's negative or you have a y-intercept that's positive. So let's work it out. Y-intercept occurs when x equals 0, boys. 0 minus 2, 0 plus 1, 0 minus 3. That becomes negative 2 times 1 times negative 3. What's my answer? 6. It's a positive 6. It's clearly up here. So once you put in that point at 6, clearly it can't be the green graph. So even if you didn't use the sign diagram, even if you couldn't read it, just by following the steps, y-intercept, x-intercept, you should be able to follow it and say, all right, well, the graph must then look something like this. One mistake that I see students do is this. Don't do this, okay? So this one, the way I've drawn it, that's okay. Don't do this. There's a tendency students to do that. You're assuming that the y-intercept is the turning point. We don't know that. Okay, so because we don't know where the turning point is, don't assume that. Draw it as if you didn't know. It just happens to cross through that, comes back down, comes back up. Okay, I just don't know where those turning points are because we haven't taught you calculus, so you can't find those turning points, and they won't ask you that in the first semester. So the first semester, you just need x-intercept, y-intercept, the correct direction of the shape. You get your 3 marks. Oh.
The other way around, we assume it's another point.
Yeah, that's correct. Yeah, so it could be there too. Most times it isn't. So that's why I just prefer that most students don't start like that, because by the time you learn calculus, I see a lot of students doing turning points here. So I don't want that habit coming through. Just draw it through, because we don't know where the turning points are. Most times they're not exactly at the y-intercept. Okay? So this one's meant to be the easier one because it's already factorized for you. 3 x-intercepts, y-intercept, x-intercept. That's 6f. So 6e was just left, right, up, down. This one doesn't have left, right, up, down, but you can read x-intercept, y-intercept. Let's try another one. Notice the shape. It's an N shape and it crosses 3 times because you have 3 brackets. What about this example? How many brackets do you see in this one? How many brackets? 2. This is 1. And I know I didn't put brackets on that x squared. I didn't put brackets on that x squared, but technically it's an x squared there. Now, if you put a bracket on where the x is and I ask you where are the x-intercepts, you can already see here, if I let y equal to 0 to find the x-intercepts, you can probably figure out a couple of things now. If y equals 0, you have x squared times x plus 3. Now this one, you know, x-intercept is at where? Where's x-intercept? Minus 3. Very good. But then what about this one? So last term, chapter 3, a lot of students missed out on this one. What should the x-intercept be? 0. And that's why a lot of students missed last term. But I bet this term you're going to pick up much better because it's after practicing, you get better at this. So you notice that this has a factor at x equals 0. What did I tell you at the square again? Putting a square at x or x equals 0, what does that mean? What's this square do again? Remind me. What's this little square do again? Anyone remember? What's the square do? So this is cubic. It's meant to have an N shape, but there's only 2 brackets, so it should only touch twice. So what happens with the square? Beautiful. It should have a quadratic. It should turn right at x equals 0. So let's look at the x-axis. You told me it's at -3. It's at 0. Now we know it's an N shape because it's currently x squared times x is a positive x cubed, so it should go up. But which way does it go? Does it go like this? Or does it go like this? It crosses through 3 and then comes back up. Now again, this one gets a bit harder because if you just found the y-intercept, they both share the same y-intercept, so you can't really tell which one it is. This is where the sign diagram comes in and it's helpful. Or you use what I've been teaching you to analyze the function. The square tells you there's a turning point at x equals 0. So it's not a turning point at -3, it's a turning point at 0. So that's why the blue graph cannot be correct. It has to be crosses through -3 because that's a linear factor. A quadratic factor will make it have a turning point. Okay, so it crosses through -3, turning point at x equals 0. Had it been the other way around, had I gave you instead x times x plus 3 squared, then that would have been the other one. That would have been turning point at -3 and cross through 0. Does that make sense? Okay, so wherever that square is, there should be a turning point. So 6e was 1 bracket, 1 x-intercept. 6f, we've seen 3 brackets, 2 brackets. 2 brackets should only have 2 x-intercepts. And in this case, to find the y-intercept, which you can already tell the y-intercept has to be at 0. How do you know? Test it again. Y is equal to, let x equal to 0, 0 squared times 0 plus 3. We can already see 0 times anything is 0. Does that make sense? X-intercept I just figured out for you. You could have used the sign diagram, which I'll teach you next session. Right now, I just want you to analyze the equation. But so far, is that straightforward? Most of this, we haven't even used 6b, 6c, 6d. This is meant to be the easier ones to sketch. So 6e and 6f, it's about you analyzing the equation. Let's try the next one. All right, next one now. up the ante a bit. How many brackets do you see? How many brackets? Well, it looks like 2, but it could be 3 because it depends on this, doesn't it? That quadratic factor. So now, this is where chapter 3 comes in. Can we factorize x squared minus x plus 1? And what's a quick way to find out if you can factorize it or not? Anyone remember from chapter 3? What's a quick way to know if you can factorize that? Yeah. Find a discriminant. If that number is negative, you know there's no x-intercepts. If it has no x-intercepts, you can't factorize it. Yeah? So let's do a discriminant. Let's remind ourselves. Let's check if it has any x-intercepts at all. So discriminant, b squared minus 4ac, if you've forgotten how to find the discriminant. B, what's the number for b? -1, very good. It is the number in front of x, so -1 squared. Minus 4 times a, what's my a? 1, very good. What's c? 1 as well. And so this gives you now 1 take away 4. 1 take away 4 is -3, so what does that mean? If discriminant is less than 0, which means it's negative, what is? No solutions. So even though we have 2 brackets, this one's not factorizable. There should be no solutions, meaning there's not going to be an x-intercept here. So how many x-intercepts should there be then? Well, how many x-intercepts am I going to get? 1. That means this here is going to get you an x-intercept at -2. So it's 1 intercept. So why this weird quadratic? It's likely got to be an N shape, but looks like this. You can see how it doesn't touch the x-axis? That's what it means. Okay, so at -2, it crosses. And then this is where you have to then find the y-intercept. Does it come up here? Does it come up here? Does it come up here? We don't know yet. But likely, that turning point will not touch the x-axis. We know it's not a inflection point because otherwise it would have been a cubed. So it doesn't have an inflection point. It must look like an N shape. And the N shape, I just don't know where it is. So let's prove it. I'm going to test it now. Let's do on Desmos. Let's see if our theory is correct. We're going to go to Desmos so you can visualize it. And then if you can visualize it, from there, you'll feel a bit more confident with sketching in exercise 6F, which a skill sheet I've given you. So y equals x plus 2. That's a linear graph. And then we had x squared minus x plus 1. See that? Still crosses through -2 like we said. Should have been 1 x-intercept. But it is an N shape. I just didn't know where the other turning point is. But I knew it wasn't touching the x-axis. So that could occur. Okay, so when you look back, those are the hints. How do I know what shape it looks? Well, I need to find the y-intercept. X-intercept, I already found out it was at x equals -2. Y-intercept, let's test that. Let's find y-intercept. So y-intercept is when x equals 0. So you got 0 plus 2. 0 squared minus 0 plus 1. That gives you 2 times, what's that? 1. So it's at 2. So that means the y-intercept is right there. And who knows, it could curve towards that, but it's an N shape. Because it's an N shape, I would have assumed something like that. Okay. So that one was the tricky one, but that's about it. That's 6E, 6F. How did that feel? You got one that moves left, right, up, down in 6E, and it looks like it has an inflection point. Then in 6F, there's a variety of ways that you can draw an N shape. Okay, you can cross 3 times, you can cross twice, you can cross once. Those are the 3 different examples, and the better way to practice is that sheet that I gave last session. I don't know if I've got any spares. Oh, I do. I've got some spares here. This one. Practice this one. Summarizes your exercise 6E, 6F. There's a variety of them. Have a go with them to see if you understand what I've been trying to teach. And that's pretty much the last time I'm going to teach your sketching bit. Okay, so you still need to know polynomial division, remainder theorem, factor theorem, how to solve, now how to sketch. There is one part I haven't taught you guys, which is called rational root theorem. But once you guys can sketch, then when I go back to it, it makes a lot more sense. Okay? But if you'd like me to teach you in this session, I can teach you individually what rational root theorem is if you're confident in all of that. Cool? And then we're back on track. We'll go on to 6i, we'll go to applications, all that. But you need to know how to do this first. E, F, B, C, D. Okay, B, C, D, E, F. Or B to F. All right, Tim, I'm going to stop the video there.